Hello, welcome to Chemistry. I am your instructor Dr. Suhasgawali and I will be teaching BSc 5th semester Physical Chemistry course on Photochemistry. So here is the outline. This is lecture number 2. In this lecture, I am going to cover about Jablonski diagram, which is very important from point of view physical photochemical processes. Second point is qualitative description of fluorescence, followed by qualitative description of phosphorescence, then non-radiative processes, in that internal conversion and internal system crossing. These are going to cover in this lecture. So let's start with Jablonski diagram. So Jablonski is a name of scientist who has given the all absorption and emission of radiation in corresponding molecule. So the electron can jump to any of the higher electronic states depending upon the energy of photon absorbed. So whatever the photon is getting absorbed into the molecule, that molecule is going to in higher electronic state. So that is because of just electron is getting jumped to the higher state. So we get a series of singlet excited state. When it gets to the higher electronic state, we say it's singlet excited state. So that can be any n number of things, that is n can be 1, 2, 3 or 4. Thus S1, S2 and S3 etc. are known as a first singlet excited state. S2 will be the second singlet excited state and S3 will be the third singlet excited state. The electron can jump to any of higher electronic states depending upon the energy of the photon absorbed. Then we get a series of triplet excited state. So it can go either singlet or triplet at higher electronic state. That will depend on how much energy is getting absorbed. So what was the energy of photon? So here Tn is represented by Tn, and n can be any integer number 1, 2, 3 and 4. So here T1 we call it a first triplet excited state. T2 is considered as a second triplet excited state, and T3 is considered as a third triplet excited state. So this is the kind of naming of that energy levels. Now we are going to see the what is mean by singlet excited state. So singlet excited state has a higher energy than the corresponding triplet excited state. So in Jablonski diagram, singlet state will be S1 will be always greater than the T1, that is triplet excited state. So this is the 100% will be higher. So that's why energy of singlet will be higher than the triplet, corresponding triplet. So S1, ES1 is greater than ET1, ES2 is greater than ET2 and ES3 is greater than ET3. So on absorption of light photon, the electron of absorbing molecule may jump from S0 to S1, S2 or S3 singlet excited state. So depending upon the energy of the light photon absorbed. So which light are you using? So that much energy will absorb and it will go to the higher electronic state, electronic energy state. So it can go S1, S2 or S3. So for each singlet excited state, that is S1, S2 or S3, there is the corresponding triplet excited state. So T1, T2, T3 etc. for the molecule. So this is the general Jablonski diagram. So here is your S naught state, that is your almost ground state. So here S1 and S2. So as the energy of photon is there, if higher energy is there, it will go to the higher energy state S2 or S3. So this is the absorption graph. So if your energy is less, then it will go to the only singlet S1 state. If energy is higher, it will go to the S2 state. So we call it, this graph is absorption. So there, these are the singlet excited state, higher energy state, and these are the T1 states. That is the triplet state of the corresponding molecule. So triplet energy state, as you can see in this figure, it is slightly lower than the singlet state. So this is always be there for each and every molecule. And the small energy levels are nothing but the vibrational energy levels, so it get relaxed at this stage. And if S2 to S1 state is getting, we call it internal conversion, so that we are going to see in upcoming slides. So this is for photophysical processes. Now we will see non-radiative processes. So in that we will be having internal conversion, that is IC, and intersystem crossing. So what is non-radiative processes? So whether in singlet or triplet excited state, it is said to be activated. So if molecular get in higher energy level, we call it singlet or triplet. Then we denote as a naught, so that is initial reactant. If it's absorbed H nu energy, so we call it A dagger. So this is A dash, nothing but your activated species. So that is the excited. That can be singlet or triplet. So A naught is in ground state and A star, that molecule, is in excited state. So the activated molecule return to the ground state by dissipating its energy through the following step type of processes. So when it comes to ground state, from excited state to ground state, it has various number of pathways. So in that, non-radiative pathways are there. We call it non-radiative transition. So what happened in this transition? So these transitions involves the returns of the activated molecule from the higher excited state S3, S2 or T3, T2. So it can go to S3, S2 or T3, T2 after absorption of any photons to the molecule to the first excited state S1 or T1. This transition do not involves the emission of any radiations and are thus referred to as non-radiative or radiationless transitions. So that's why we say it's non-radiative transitions. The energy of activated molecule is dissipated in the form of heat through molecular collision. So now everything is in solution form. In solution, energy can be dissipated in the form of heat. So that is because of molecular collision. So we call it, this process we call it internal conversion. So and occur in the lifetime of this for this process is 10 to the power minus 11 second. So this is very uh, fast process. So this is happen because of molecular collision. Now second non-radiative transition is intersystem crossing. So in this process, the molecule may also lose energy by another process called intersystem crossing. So this process involves transition between states of different speed. So speed can be parallel or anti-parallel. So due to this different multiplicity, this intersystem crossing can happen. So for example, S2 to T2 or S1 to T1. So spectroscopically, such transitions are forbidden, but this is happening, and due to this, energy losses are there. So that's why we call it non-radiative transitions. So as you can see in this figure, so this internal conversion is this one. So S2 to S1. So this is internal conversion. And if this is happening, triplet and S1 state has different spin multiplicity as we have seen in last lecture. So triplet means your spins are parallel, and singlet means your spins are paired, means it's anti-parallel. So this transition, if it's happening, we call it inter-system crossing. So these are the two different systems are there, but same molecule. And if this transition happens singlet to triplet, we call it inter-system crossing. So this process is, it's a non-radiative process. So there is no emission of any photons. Now we are going to see the qualitative description of fluorescence. So fluorescence is the process that we are going to see in now. So the radiative transition. So far we have seen non-radiative transition. Now we will see the radiative transitions. So what is radiative transitions? So these transitions involves the returns of activated molecule from the singlet excited state S1 and triplet excited state T1 to the ground state S0. So if your any molecule is in T1 or S1 state, if it is coming to the ground state, we call it radiative transitions. So these transitions are allowed transitions spectroscopically. So the emission of radiation in this transition, we call it fluorescence. So the lifetime of the fluorescence, the order of about 10 to the power minus 8 second. So this is slower than the non-radiative transitions. So as you can see in this figure, so from S1 to S0 state, any vibrational state of S0 state, we call it fluorescence. So if transition happens from S1 to S0, we call it fluorescence. If transition happens from T1 to S0, we call it phosphorescence. Now we will see qualitative description of phosphorescence. So the transition from triplet excited state T1 to the ground state S0 is rather slow since it is forbidden transition. So the emission of radiation in this transition is called phosphorescence. So the lifetime of phosphorescence are much longer, being in the order of 10 to the power minus 3 second or greater. So compared to all transition, these radiative transitions means phosphorescence is a very slow process, and that's why it has higher lifetime. So since the transition involves spin inversion, which needed time for its occurrence. So in phosphorescence, your spins are parallel. So to get at, we know at ground electronic state has all spins are paired. That's why it takes time to get invert. That's why this transition is forbidden transition. So both fluorescent and phosphorescent radiations are shorter frequency than the exciting light. So as you can see in this picture, T1 to S0. So this transition, at this stage your spins are parallel, and to get it down at ground state you required corresponding more time than the fluorescent processes. So that's why phosphorescence is a slower process. It requires 10 to the power minus 3 second to the 1 second. So this transition we call it forbidden transition. So this process will always occur from T1 to S1 S0 state of the corresponding molecule. And as you have seen, the distance between these energy levels is higher compared to T1 and S0 state. So if energy gap between T1 and S0 is lesser, so your frequency has to be shorter and wavelength should be longer. So that is the directly proportional. Now we are going to see the representation of these photochemical processes in Jablonski diagram. So all radiative and non-radiative process can be easily shown by using Jablonski diagram. If a molecule absorbs light, following photophysical pathways are possible. So this is the Jablonski diagram and these are the processes. So first process is absorption of light. So that is absorption of light is transition from S0 state to the S1 state or S2 state, that is singlet excited state. So this is only happens when your absorption of light is taking place. The second photophysical pathway is from S1 to S0. So this transition is, we call it internal conversion, or this from S2 to S1 or S1 to S0. If it happens, we call it internal conversion. So this is the second process. Now third process is fluorescence. So in fluorescence, from S1 to S0, this transition take place with emission of radiation. So this is a radiative transition. So that's why we call it fluorescence. So fluorescence of photon of fluorescence molecule, fluorescence we denoted by V nu F, that is the frequency of fluorescent molecule. Now fourth transition is from S1 to triplet state T1. So this is non-radiative transition we represent by intersystem crossing, that is ISC, from triplet to S0. If this transition take place, this can be happen two way, either radiative or non-radiative transitions. So if it is non-radiative transition, then it is a intersystem crossing, that is IC. If from T1 to S0, if transition happens with emission of light, that is radiative transition. If that emission happens, we call it phosphorescence, that is represented by H nu P. So here nu is the frequency of the phosphorescence process. Seventh transition is the from T1 to S1. So this can go reverse. So this is the reverse intersystem crossing. And after reversing, if that S1 state comes to the ground state, that is S0 state, we call the delayed fluorescence. So this is also radiative transitions. So in this case, you will get the photon emission. So we denoted by H nu ED. So here is the delayed fluorescence. So now we will see the chemical reaction, photochemical reaction. So the activated molecule may also use energy by undergoing chemical reaction. Since the molecule in singlet excited state returns quickly to the ground state, it gets no chance to react chemically. So as we have seen, fluorescence process, so these transitions are very less or very uh, fast and take less time. So that's why at this excited state, your singlet excited state, your reaction doesn't occur photochemical reaction doesn't occur. However, if molecule is in triplet excited state, return to the ground state comparatively slowly. So this provides ample opportunity to the activated molecule to undergo chemical reaction. So triplet excited state is crucial energy state to get react with other molecule. So this is very excited state of molecule, and as we know, if your spins are parallel, so it is very reactive. So it is very special to get undergo chemical reaction. So these are the references, and for images and for content these are the books, so student can follow this. So here we came to end of this chapter. uh, Hope you like this video. So thank you for kind listening. See you in next lecture. Till then, happy learning.